Okay, so it's time to start talking about projectile motion, which is our first use of two-dimensional kinematics. So to start the unit, we're going to just draw a visual, a motion diagram of an object in projectile motion. So I'm going to sketch it, and I guess I'm just going to have to ask you guys to trust me that this is what a correct motion diagram should look like. But I think you'll probably have an easy time doing that because I think you're probably used to this like parabolic path that you've seen balls take. Where they go up, they slow down, and then they come back down. So this is the idealized version of a projectile's flight. This is assuming that there's zero air resistance, that there's nothing funky about the ball. I guess that kind of comes into air resistance, but there's no kind of spin on the ball that does some other weird stuff. There are definitely other things that projectiles can do. We're just going to deal with the ideal of a ball just flying through air, basically absent any effects from the air. And I guess I'll try and come back and or in a moment, I'll talk about what would be different if it was in the air, or one of the primary differences. So if this is the motion diagram, then we have all those positions that are taken at some kind of snapshot rate. And if I draw in the velocity vectors, sorry, that one's a little curved, but whatever. We have all of these velocity vectors. And just there by itself, nothing right away jumps out at us. But if I start breaking it into components and I start doing horizontal pieces and vertical pieces, something very interesting and important should hopefully jump out at you. So the reason why I'm doing this live in front of you is because I'm hoping that you'll make the observations on your own. So I'm drawing in the horizontal only vectors. These are the vectors that like this ball is going to its new horizontal location. So that gets that one to there. And then this one it would go along there, and it goes along there, and it goes along there. So along the way, this turns into that horizontally, 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 and this turns into that horizontally. And if I do a similar job with the vertical vectors, I say that, okay, from that horizontal, I also went up, and then I went up again, and then I went up, and then here I'm just going to mark it with a 0 because it actually didn't change height. And then for this one, it's going down, going down, going down. And I'm hoping you're noticing already by yourself some of the key observations that you can make here. The first observation, let's write this in, key observations. The first observation I'm going to write in blue because it has to do with what's happening horizontally. And I'm hoping you've noticed that our horizontal velocity is constant. That's an observation, but I can give you a little bit of the explanation as well. As long as there isn't air resistance, we would expect that since nothing's pushing on it horizontally, making it go faster or slowing it down, it should always keep going the exact same speed horizontally. Then our next observation, I'm going to make in red because it's an observation based on what's happening vertically. And I'm hoping you've noticed this, but from a vertical perspective, we should notice that we have a vertical acceleration downwards. Now this is, again, idealized, so we can't really read anything into the amount that it's going down, but I will point out, okay, it's going from 3 units to 2 units. That was a change of 1 unit, 2 to 1, change of 1 unit downwards, from 1 upwards to 0, again, a change of 1 downwards, from 0 to -1, a change of 1 downwards, -1 to -2, change of 1 downwards, -2 to -3, change of 1 downwards. So, we're noticing that we always have that vertical acceleration downwards. So those are kind of the key observations that I want to make. Before I move on too much, let's just address what air resistance would do. Air resistance actually does affect the horizontal velocity. And so what's going to happen is it's going to be slowing down, and we would tend to get a path that looks a little bit more blunted like that, where it has the nice parabolic shape at the beginning, and then it starts curving down faster and faster and faster. This is incidentally part of what it's what happens with every ball, but actually dimpling a golf ball lets it keep a straight flight longer, but then it actually slows down even faster. So you get a little bit more distance out of a dimpled golf ball than you get out of a normal ball. But that doesn't really have anything to do with this course ever, but it is kind of, I don't know, interesting to me. So we talked about air resistance a little bit, but I wanted to point out those key observations. And I guess the last observation, and this I guess is obvious from the first two, is that we have a difference in horizontal and vertical behavior. So those are key observations that we need to make about projectile motion. And then up in this top corner, hopefully I can fit it in, I'm going to actually write our projectile motion rules. Just for the sake of brevity, I'm actually going to pause this and write in the full rules one by one. Hold on. Okay, so that observation leads us to the conclusion horizontal velocity is always constant. That is, of course, in the absence of air resistance, but you'll basically never be asked a question that requires you to do anything mathematical that has air resistance. So conceptually, we've already covered what air resistance does to projectile motion. And so our projectile motion rule is being stated for when you're trying to solve problems, most problems that they give you in AP Physics where air resistance is negligible. And that would, then this rule holds that horizontal velocity is constant. Okay, I'm going to write the next one out. So for our next rule, we say that vertical acceleration is always the magnitude of g, so that's free fall acceleration, and it's always oriented downwards. Now, any thrown object, any object in projectile motion is in free fall because there's only one force acting on it, the force of gravity. And if that's true, then we know already that the acceleration should be g, and I said that the direction was downwards instead of saying it's negative g, because the decision about whether it's positive or negative is going to be based on your own coordinate system. So that's rule number 2. Our next rule is that what happens vertically has no effect on what's happening horizontally and vice versa. This is the Las Vegas rule of projectile motion. What that means is if I went to a different planet and threw this projectile on the other planet, I could still have it going at the exact same horizontal velocity, but it would slow down much faster or speed up much faster along the horizontal or the vertical axis because what's happening vertically has changed, but that would have no effect on the horizontal. Or I could throw a ball much harder horizontally, and it would still have the exact same amount of time in the air as the object that was thrown at a lower speed, but at the same vertical speed. So keep them separate. Don't try and assume that just because something's moving fast horizontally, that it's going to have any effect on what's happening to it vertically. Finally, our last rule is that time is our unifying variable. The amount of time that the ball is in the air is determined by the vertical equations and the vertical velocity. But the minute that it hits the ground vertically, it's going to stop moving in projectile motion horizontally as well. So when you're doing problems in projectile motion, you will almost always solve a horizontal problem first in order to solve for the time or the time variables that determine how long it's in the air. And then you'll use that time or time variables to figure out how far it's able to go over in the horizontal direction. All right, that finishes our projectile motion observations and rules. Now let's do a little bit of trig in the next video.